Hmm. Why does it not record? Okay. All right. So we're going to revise magnetism, and this is take these as set of facts for now because we haven't derived magnetism yet, right? There's a lot of things we need to cover to fully understand magnetism. To fully understand magnetism, one needs to understand quantum mechanics as well. So we would have to come back and cover the gaps again. And some of it I have already covered when we were covering the quantum mechanics concepts, right? So you're all familiar with magnets, right? We all played them as children. They have a north and a south pole. Let me swap the magnet around here. Oh, here it is. There's a magnet here, right? There's a north pole and a south pole. And this is a special variety of magnet. This is a permanent magnet. All of the magnetism in this is actually coming from the electrons. It's really weird. There are no actually rotating currents in there. It's actually electrons, unless you say electrons are rotating currents, but then electron has no sense. So this is your run-of-the-mill fridge magnet, the magnet that you play with as a child, is actually already a quantum mechanical object. It has got electron spin contributing to the magnetism. Okay, so that's the first variety I'm showing here. You know, this is the magnet, and you get the north to south magnetic field lines. What do magnetic fields do? We will come back to this after the summer project, when I will go back to explaining electric fields and magnetic fields and how they are basically one unified field. Okay, but we're kind of skipping everything and jumping to something practical. Okay, you can make a magnet in a different way. You can make it by making a electromagnet. An electromagnet may have a permanent magnet at its center, or may have a paramagnet at its center, and you basically apply current into it, and the direction of the current and the amount of current produces a magnetic field out of it. Okay, very simple, right? Currents in loops, actually currents produce magnetic fields, period. But you can have current, you can have a magnetic field without current. There is no current in this one, right? There's no current to this. But it has a magnetic field because internally the electrons are producing the magnetic field. You understand? Okay. So to be, okay, I have an example here. Watch this one. This is the a very child-friendly toy that we were playing with. Let me change to, can you see my screen? Right? So a motor has, you know, this guy here, which is, this is an electromagnet. It has something ferromagnetic or paramagnetic in the center, and the copper coil is producing current through it, and that makes it a magnet. This is a magnet. And then you take a permanent magnet, put it between here. Sorry, the wrong way. Magnet has to be put this way. Anyway, this doesn't work. It's very badly made. It doesn't have enough, it's not low friction enough. And the magnet is producing a magnetic field through the center, right? It's producing magnetism through here. And that magnet and the central magnet interact to produce rotating torque, right? But my point is, this is a permanent magnet. This is formed by the electron spin that's producing the magnetism. And this is a different type of magnet. Here, the charge that's going through the coil produces magnetism. Okay. So strictly speaking, there's like one more type of magnetic field, magnetism, that's produced because of related but slightly different effect. So let me cover that first. So you got your three varieties. The electromagnetism, which is because of current going through coils, right? Going through, you know, you need to put something in the center to kind of amplify the field, and you get magnetic field already. That is electromagnetism. Then you have the the angular moment, and so these two are both angular moments, so I have to be careful. This is due to the rotation of electrons around the nucleus. In chemistry, you must have learned something called azimuthal moment, right? This is the azimuthal moment, m times m plus 1. Okay, they're all related fields. Chemistry and magnetism are related fields. But this is because an electron goes around the nucleus, and that looks like a current, right? Because the electron is rotating around the nucleus. It's essentially a current. That's the second type of magnetism. It's very rare. I think one metal like gadolinium has this. And then you have spin magnetic moment, which is coming because the electron has a spin magnetic moment. So you just take an electron, put it somewhere, right? How do you create an electron, Wari? Wari, do you know how to create an electron?
No.
Wasn't there like if you decay some, it's like beta decay or alpha decay, right?
I don't need to go that far. If you comb your hair, Wari has a lot of hair, make it dry, and just do this, scratch, you're going to create some free electrons in there. So making an electron is actually relatively easy. Many materials just give out electrons. Like if you put a metal outside in the sun, it will give out electrons. That's called the photoelectric effect. So you take an electron, you do nothing to it, right? There's no spin, there's no current going through it. It's just by itself, right? And you know, to put a current in a loop, you have to have a battery, and the battery has to keep driving. But an electron, nobody's running a current through it. It just exists by itself. And that produces a spin magnetic moment. So those are three varieties of magnetic moment. All these three are unified. It's not like, you know, it's not a primitive description of magnetism. All this magnetism is somewhat well unified into one unified theory. So basically, currents produce magnetic moments, and electron produce magnetic moments, or particles produce magnetic moments, even though they don't have running currents. Okay, and I'll explain to you when we cover quantum mechanics. And those of you who have taken this, who had some of the quantum mechanics I explained, may actually already understand some of it. Okay, so there's a magic source of magnetic moment, which is an electron. So there are many particles which have magnetic moments. Electron definitely has it, right? So the amount of magnetic moment an electron has is called a Bohr magneton, B-H-O-R, Bohr magneton. It's actually a very weak magnetic moment. An electron has a very weak magnetic moment compared to its charge. Magnetism is much weaker than charge for a reason, right? And I'll explain to you in later class. Okay, how much is a magnetic moment? It's 10 to the power minus 24 times 9, so we can practically call it 10 to the power minus 23 joules per Tesla. That means that a Tesla of a magnetic moment produces an amount of energy which is 9.2 times 10 to the minus 24 in a single electron. So that's a very tiny amount of energy, right? So what does that mean? It means that in order to produce 1 joule of energy, in order to expend 1 joule of energy, you need 10 to the power 23 electrons in a 1 Tesla magnetic moment. That's a huge amount of magnetic moment and a huge amount of electrons. This is a lot of electrons to produce 1 joule of energy. Okay, so magnetic moment is a very weak number. Electrons magnetic moment is a very weak number. And this is one of the attractions of doing computing with spin, but also one of the drawbacks of doing computing with spin. So we'll come back to it. Okay. So I said there are 3 types of magnetic movement: electromagnets, the rotation of electrons around the nucleus, and the spin of the magnet itself. Okay. I'm kind of giving you the facts because I'm not explaining to you how to derive the magnetic moment of an electron, right? That requires two steps. One is to understand that if I take a charged body, right? Take any charged body and rotate it, right? When you rotate it, rotating bodies have angular momentum, right? And that comes from moment of inertia times the rotation speed, right? And we have done this before, right? Moment of inertia of a ring is mr square. Its angular moment velocity is omega. Angular momentum is mr square omega, right? It also has a magnetic moment, which is given by current times area. Now that there's if you sit here and watch every cycle, charge q passes through it, right? Every rotation charge q passes through it. So you can treat it as if there's a current going through the piece, right? So if I calculate the equivalent current, which is charge divided by the time period, multiplied by the area, I get the magnetic moment, okay? If I take the ratio of magnetic moment to angular moment, I get a number, q or 2m. And the beauty of this is it's independent of the shape of the object. You can take a potato, you can take a peanut. If it's uniformly charged and you spin it, it always has a ratio of magnetic moment to angular momentum of q over 2m. Okay? But it needs to have a moment of inertia to have, it needs to have shape, some shape for the charge to act like a loop of current, right? But an electron has no size, right? I can argue an electron has infinite size because its influence is felt at infinite distance, right? But I can also argue electron has no size because I can go any arbitrary amount of distance close to an electron. I can do that to a proton, I can do it to a neutron, can't do that to a nucleus, right? But I can go, if I have a lot of force, I can make the electrons literally sit on top of each other, right? So electrons has a size which is undefined, basically undefined, right? I can argue both ways. It's either infinity or it has no size. So because of the analogy with the proton, which has infinite influential space, but there is a certain size of a proton, let me make sure that physics hasn't changed since the last check. Yes, the proton actually has a size, but an electron doesn't, right? And have to be careful. With the Large Hadron Collider working, you never know how when the size has changed, right? Okay, so a proton is also a unit particle, but not a unit particle, but a particle, right? A proton, two protons repel at any distance, right? So you can argue protons are infinite size, but that's not really the case. You can bring two protons close by only to the extent there's a limit after which two protons cannot be crushed together. Okay, so a proton has finite size. So with that analogy, now you have to say electron has no size rather than it has infinite size, right? You see the logic? Anyway, I'm going to jump a little faster and we will come back to it. You need to listen to this lecture a few times. So with the similar, okay, let me see if so this is perhaps the most advanced concept today, which is that the ratio of the magnetic moment to angular moment magnitudes of any oddly shaped mass with uniform charge is basically Q over 2m. Okay?
Actually, what is the significance of like finding that? Like, what is this?
The ratio?
Yeah.
Well, in physics, we always like to find universal things, right? It's kind of like, okay, the whole idea is that are there universal laws, right? We're trying to look for transferable learning from one part of physics to the other part of physics, right? So whether you're a biological system or a chemical system or a physical system, energy always comes out, right?
Yeah.
So that's why we That's what we call as physics, rather than the details of right.
But like mathematically, what is like the ratio of, what is it? The magnetic, what was it
M
saying?
is magnetic moment,
Mag-
which is the current times area
okay.
of a loop. And then L is angular moment, which you know is I times omega, which is the integral of mr squared. Right? We have done this extensively, right?
Yeah.
It turns out there's like a universal constant, doesn't matter. If I take your head and uniformly charge it and I spin your head, I get the same ratio. That's why it's kind of, like there's something cool about it, right?
Yeah.
The same relationship between angular moment and magnetic moment. And they're completely, like, one is a mechanical concept, right? Other
Yeah,
is a,
that's why I was wondering.
right? Why?
Why is it? Wait, why is it Q over 2m and not Q over m?
Aha. There you go. There's like, so if I do this, so this ratio is called gamma. Gamma is Q over 2m, okay? Which is the ratio of magnetic moment to angular moment. Angular moment of an electron is actually h bar over 2, and this comes from quantum mechanics.
Okay.
In our, when I come back to do revision of quantum mechanics, I will argue why, right? Why it is h bar over 2, or why there's angular moment for, why quantum mechanics means angular momentum. You remember we have argued this at some time, right? Because if you have a constant angle, you have violated quantum mechanics, right? So you can't have constant angle. That means you're rotating. If you're rotating, you should have an angular momentum. And therefore you have a minimum amount of angular momentum that's required by the uncertainty principle. Okay, all said and done, an electron has an angular momentum h bar over 2. Okay. Oh, okay. Let me apply this rule. So I will apply this rule. Gamma is equal to m over L. M of an electron is therefore equal to gamma times L of an electron. So charge and mass are known, right? And the angular moment of electron is known. So you get Q over 2m times h bar over 2, which is electron charge over h bar over 4m. That should give me the angular moment.
Wait, and is it the vector value of the magnetic moment or just the
Angular moment is a vector. That's why I keep saying, but this is the magnitude of it. Okay.
Wait, but like you said, gamma equals Q over 2m equals magnetic moment over L. Is that vector or scalar, or does it not
These are
matter?
all vectors.
Okay, okay.
Yeah. So I don't
They
know.
will be pointing. They'll be pointing in the same direction, right? The
Correct.
two vectors. So
Unless
when you
the
divide
charge
it,
is
it becomes
negative,
scalar.
then the reverse. If the charge is negative, then the reverse.
Okay. Yeah.
Okay. So great. So just because this applies to Anushka's head, to a potato, to a peanut, to a football, I should just not care about electron shape, and knowing mass and charge, I should find the magnetic moment, right? And I get a magnetic moment, right? This is exactly off by a factor of 2.00 something. So everything other than the electron follows Q over 2m. But when you go to an electron, I have a discrepancy of a factor of 2. And to understand where the discrepancy of factor of 2 comes, you have to learn quantum electrodynamics. Okay, this is the thing about beauty of physics, right? The rules are universal till you hit the next universal phenomenon, right? So electron follows the same rules as mesoscopic objects, but it doesn't follow the same number. It follows a slightly different number. So it's the same rules, but then the rule is the actual number is different. And to find that actual number, you have to learn quantum electrodynamics. So it's one of the first places where you kind of get a glimpse of, you get a glimpse of quantum mechanics because of all the things we speak about, right? Wave functions, the atoms.
Wait, but how did they experimentally measure that?
Oh, you can, there are some very good measurement experiments. I can come and cover or something.
Okay.
Okay. Electron charge was measured by Millikan in an oil drop experiment, which you can set up in your garage. Electron spin is much weaker than the charge, so you have to do a little bit more extra work to get the value of the spin of an electron. Okay, you guys understand it now? So anything mesoscale, which is large scale, the ratio of magnetic moment to angular momentum is just pure 2. But when it goes to a very, very small point object, such as an electron, it needs a factor of 2 on top. And why the factor of 2? You would have to go through like a year of quantum electrodynamics to understand. Okay? Okay, so now let me rewind and simplify. Let's go back to our fridge magnet. It's not a fridge magnet. This is a magnet that's made in China, which my son bought to play with the toys. So it's got a north and south pole. Magnets are usually metals. It's very unusual to have a non-metallic magnet. Insulating magnets are very rare, but some other time we're getting into the details of the of magnetism here. So this is a magnet, right? Magnets are usually metals, right? So now I need to tell you what metals are. Metals are basically sea of electrons. It's basically sea of electrons. All the beautiful internal details of the material disappear, and you basically have like waves of electrons. Metals are basically seas of electrons. You know, the thing about a sea is these electron waves shouldn't be seeing the atoms. If the atoms are seen, you don't get a sea of electrons, right? The beauty of a metal is that the electrons kind of glide over the atoms. Like the atoms are there, but the electrons kind of glide over the atoms. That means one electron coming from this iron atom is able to transfer to this place without a lot of effort. And then one electron from here goes here without a lot of effort. They kind of like you know, it's like everybody just, you know, got in love and lubricated the electrons, and the electrons left the lattice and they're just bouncing around, right? That's what a metal is. But the electrons don't leave the surface usually, right? If you heat a piece of metal, when it's red hot, it does leave electrons out. It does produce these electrons. So if you remember, if you have ever seen these electric heaters that are very common in India or in places where central heating is not there, you would find that your eyes start burning because the red hot metal is giving out electrons. And it kind of makes the room very nasty. It's all like charged up. Especially if you have long hair, you're going to feel it. You know, it gets frizzy. It's horrible. The electric heaters are horrible. That's when the electrons leave the sea of electrons, right? If I tell you that in a permanent magnet is basically a metal, but it is a magnet, the very simple extrapolation is that these electrons they all have spins pointing in the same direction. So a permanent magnet is a sea of electrons pointing their magnetic movements in the same direction. That's what a permanent magnet is, right? Permanent magnet is simply a sea of electrons where the magnets are all pointing in the same direction.
How about a paramagnet?
Yeah, a paramagnet is a sea of electrons where the electrons are not pointing in the same direction, but the moment the external magnetic field comes, they'll all point in the same direction. So it's like, you know.
So are there more materials that are ferromagnets or paramagnets?
There are very few ferromagnets.
Okay.
In fact, I invented the 4th room temperature ferromagnet. This was in Nature some time back, out of a material called ruthenium. So there are very few room temperature ferromagnets. They are cobalt, iron, nickel, gadolinium, and then my research added something called ruthenium into this picture. And this is also in a specific phase. So there are not many room temperature ferromagnets. And then there are many paramagnets. You can make paramagnets, materials that magnetize when you put put them in a magnetic field. Okay. So the lesson I want you to take is metals are sea of electrons. Okay. What makes the electrons kind of gloss over the beautiful iron atoms is a mystery, is one of the grand mysteries that was solved in material science, right? How do I explain it? Let me put it this way. Have you ever seen a Mexican wave in a studio, in a stadium? Right? The Mexican wave goes like that, right? But in reality, these are all coming from chairs of people sitting there, right? So how do I explain this without using like complicated words? Is that the Mexican wave doesn't feel the staircases, the umbrella somebody's carrying, the various obstructions, or even the seats inside the stadium, right? Right? The Mexican wave doesn't feel that because there's a way to avoid it. If you use the beauty of wave mechanics, there's a way to avoid it. You don't have to see the internal details of all the chair structure, right? So because atoms are in uniform lattices inside metals, the electrons' waves are able to do that. The electrons' waves just gloss over all the obstructions. That's what makes a metal a good conductor, right? The electrons are literally like a liquid, and that is called a Drude gas. They're in a liquid, so almost like a gas state. So they not a liquid. Liquid means a special thing, right? Liquid means surface tension. So this is described as a Drude gas. So the electrons are like a gas, and the moment you push on it with the electric field, the gas starts moving. So that's what a metal is. In a ferromagnet or a magnet, these free electrons are still free, but they are all well behaved. They're all pointing in the same direction. Okay? Clear? You guys got everything? Okay. I don't want to overload you. So I will introduce the idea of, well, I think I introduced the idea of spin already to you, right? Spin is inherently connected to electrons, but spin is present for various materials, right? Anything that's uniform in charge that is rotating has spin. Remember Anushka's head. You can charge Anushka's head by rubbing on her hair, right? And she's all charged up. You're going to put her on a turntable and rotate it. Now she'll have angular moment and spin moment, right? An electron has no shape and size, but it still has magnetic moment inside it, which is that's the crux of an electron, right? What an electron is still there's no research, there's no experimental research to say this is the shape of an electron, this is the internal structure of an electron, right? We don't know how to break it, to make it subparts and then kind of come up with the size.
So is what we like think of as orbitals just like hearsay, kind of like what we think of?
So orbital is actually like a thing, right? An orbital is a thing, what an electron does around a atom. So if an atom is there, the electron has size. That's the size of the atom itself, right? So if you have a hydrogen atom, if you put a proton, the electron comes and becomes a cloud around it, and then it has a size. But if you take the electron out of the atom and you put it on the side, let's say you rub your hair, you pull the electron out, the size of that is a magical thing. Like when the electron is going around the hydrogen atom, its size is fixed. It's the size of the hydrogen atom, right? But I'm talking about the electron by itself. Like you took a hydrogen atom, you separate it into a proton H plus and E minus. That E minus, when it is by itself, right, in vacuum, has no size, right? That's what we're talking about. And even then, when it's not rotating about something, it has got a spin magnetic moment. And that's what makes, that is what contributes the magnetism of magnets. Okay, so I already started the abstract that I want to submit, and you guys have to figure out the research. So I wrote the abstract already with what the result needs to be. I know which conference we need to go to, but you have to do the work. And I don't know the answers, okay? But you have time till end of August to do this, and we need to submit it, and then in about 6 months, okay, they get accepted.
Wait, August or July?
End of August, I think.
Okay.
Submission.
Okay.
And the 12th graders, the guys who are going in 12th grade, who is going to 12th grade this?
Me.
So you get the dibs. You have to really, really contribute and get on these papers, right? And then the 11th, the remaining ones, they have to contribute even more to get on the paper. Otherwise, they get pushed to next year. So it's a little bit of competition, but you're better off collaborating rather than competing. There's no way you're going to solve it just by yourself. You have to discuss with each other to solve it. There's literally 0 chances to solve it by yourself. Okay, at least to understand and explain the concepts to yourself. Okay, now let me add one more thing. So I'm not yet covering the quantum mechanical nature of spin. I'm not covering it for now. Okay, this is for simplicity, and I will do that later. Okay, it's an unnecessary complication. The project is going to go in the way of engineering rather than the basic description of spin in quantum mechanics. So we will do it at leisure later, right? Maybe next year. Okay, so if I take a magnet is what, Abdul?
It's a sea of electrons with almost all of them in the same direction of spin.
Correct, almost all of them. Good job. Good job, Kanchana. Now, because of the shape of this object, the electron, the magnet has a tendency to only point in the, let me draw the axis, X, Y, and Z axis. X cross Y should give you Z. That's how we always write our coordinate system, right? Okay.
Yeah. Okay. I had a question about this. Is there any reason it has to be only X, Y, and Z?
Yeah, that's because of the symmetries of the cube, right? If the magnetic moment points in the non-symmetry direction, the energy of the material is not minimized. It has to
Okay, so
point,
we're assuming that we're working with like cubes that are magnet shaped, basically.
yeah, these are
I was-
magnetic
yeah,
cubes.
Yeah,
right?
sorry, magnets that are cube shaped. Yeah.
The magnetism tends to point in the direction of the length of the material. That's why you have bar magnets which point like that. And there is a, don't want to add to it, but because we are recording, there's something called magnetostatic energy which needs to be minimized. So things like to point in the long and short direction. It's very similar to if you have a tip and you put charge on it, all the charge goes to the tip of the charge.
What was the name of that?
This is the magnetostatic energy. To minimize the magnetostatic energy, you need to put it this way.
But a what?
The north and south pole have to go the farthest possible. They have to be pointing in the farthest direction possible. That's another way to put it. They have to point away from each other, like as far away as they can. So if I take a cylinder, the cylinder will have, if it's a magnet, it will point like that. If I take something like this, they'll point in the long direction. If I take cube, it will point It can point in any of the three directions and also their negative directions, right?
What about a sphere?
Sorry?
What about like a sphere?
Yeah,
Ah.
what if it wasn't like
Oh,
straight?
yeah. Okay. Don't make my life easy. A sphere can point in any direction.
So then why wouldn't we pick that?
Well, that's because we are going to do digital electronics. Digital electronics means that I'd like to have plus x or minus x. If I have a x, it should be plus x or minus x. It should either be clearly in the x direction or clearly in the y direction, clearly in the z direction. I don't want it something at 45 degrees, generally, right? But not while solving the problem. Maybe solving the problem, you need to rotate the spins at 45 and then do something else, right? But generally, I would like to represent data with saturated bits, not like intermediate bits.
If you do a sphere, you could do like continuous.
You can do continuous. That's the research paper maybe next year, the year later. Like, Spintronics is like this permanent itch you can keep solving, right? Okay, so this is all I'm going to teach. The last piece is this, and then you can just revise this video. Well, the video is not available right away. So I'll share you the PDF and you can revise between yourself. And everyone can take turns explaining this to the others and troll each other, right? Ask a lot of questions to each other, okay? Okay, the last concept for today is if I have a cube, did I fill everything? Yeah, it'll have magnetic moment x, y, and z direction. So the magnetism can take m hat means unit vector of magnetism, right? The actual amount of magnetism is m is a vector. M hat means unit vector. A unit vector is a vector divided by the magnitude of the vector. Yeah. Wari, have you taken this? Have you done vectors?
Yeah, we did a little bit of this in physics, but
Okay. Yeah. A unit vector is a vector of dimension 1, right? Okay. So this one, m hat, can be plus x or minus x, plus y or minus y, plus z or minus z. Okay. How many states are these? 6 states. So this is called sexternary logic or 6-state logic or 6 states of the magnet. Okay. So what we want to, the name of the abstract I want to submit, provided you will get to the answer. And I want the people who need to get into college to get the dibs this year. And of course, we will do more complicated version next year. Last year, we did like four papers in international conferences. So we'll see. We'll see. No pressure, guys. Okay. All right. So the problem I want to solve is if I have a magnet which has a plus x state of magnetism, I want to create a circuit which takes the magnetism to minus x. So I want to go input to output. If x is input, I want minus x as output. Minus x is input, I want x as output. Y is input, minus y as output. Z as input, so similarly, minus y gives plus y. Z gives minus z gives plus z. Okay, this is the NOT gate or invert gate. Okay, this I already know how to do. So I'll teach you next time. There's no way, there's no ab initio way to get there, but I want to see if you guys can do it. Okay, and if you can do it, I would be like, hey, we just invented new NOT gate. Okay. Okay, so the other
What are you allowed to do in the circuit?
Yeah, that's what I was wondering.
Yeah, you're allowed to do. See, this is a sea of spins, right? You can inject spins here, pointing this way into this.
Wait, so what is that diagram representing?
this is a spin channel, this is a gate. If I inject spins here, and then I can force this magnet to rotate. So this is a copy gate. But if I extract the spins, I'll get a NOT gate.
What is a copy gate?
Means if X is the input, X is the output.
Okay, okay.
Yeah. If I extract the spins, then I flip the other way, right?
So
That's
is
how
the
you get the
goal-
NOT gate.
Is the goal to figure out how to do the invert gate or how to do another type of gate?
How to do the invert gate? I already told you how to do it. You extract the spins. That's how you do it, right?
How do you extract the spins?
I just pull the current out. You put a voltage and pull the current out. I can do it. It's pretty easy. I mean, this research was only published in 2010, but I don't know what people were doing 30 years before that. I entered the field in 2010 and I was pretty like, okay, big idea, guys. Is you pull the charge current back and the magnet flips. Okay. Anyway, I don't want to make it lighter. I think the experiments lagged a lot than the concepts, right? Okay. This is the hard one. This is the really hard one. In this one, you need to rotate the spins by 90 degrees. So if I give you X, you need to give me Y. If I give you Y, you need to give me minus X. If I give you minus X, you need to give me minus Y. If I give you minus Y, you need to give me plus X. This is rotate about Z.
And is there a classical is there a gate, logic gate like this in a classical computer that can be
Nope.
comparable? No. So what would it be used for?
In order to do computation, first you need to know how to rotate between the states. It's kind of like a basic attribute of things. Like you need to be able to rotate through your.
If you're working in basics, wouldn't you want like a way of getting 0 to 1, 1 to 2, 1 to 3, 3 to like that?
This is a binary system. There's nothing above 1. It's the 0 or 1.
Yeah, I know, but we were talking about like computation would be in basics, right?
Yeah.
So the next one we need to do is so these 6 states, if they are represented by, I don't know, let me say they are, if X hat is A, minus X hat is B, Y hat is C, Z hat is D. Sorry, minus Y hat, like that. So if the symbols are A, B, C, D, E, F, right? Instead of ones and zeros, right? You would start representing numbers in the A, B, C, D, E, F notation, right?
Oh, okay.
Right? And then you will have gates and adders and multipliers based off of it. We are far from it. There's nobody who's actually done this, okay? So first, just get me a way to rotate between A, B, C, D, and so on, right? You just need to find
So
A,
that's the 4. Okay.
B, C, D, E, F are the symbols, right? A is plus X, B is minus X, C is plus Y, D is minus Y, E is plus Z, D is minus Z. And first I want to have a gate that rotates between A, C, B, D, A, and so on.
So you can have 3 rotating gates though, right? For
You
90
can have
degrees.
3 rotating gates.
Okay. And is the goal to okay. Is the goal
You
to
get as far as NOT gate, and the this gate is called half complement rotation gate. It's called half complement because instead of going from plus X to minus X, I go to plus X to Y, which is 90 degrees. And I do another time, I get, so you need to apply this gate twice to get the negation gate. So it's kind of like a square root of a NOT gate, right? You have to take this gate twice to get the NOT gate.
Okay.
Right?
I still don't understand what your solution is for the NOT gate.
I'm not telling you. I think I told you enough. You will have a
Wait, no. But with it, let's say that we figure out the logic for this half complementary gate from A to C to B to D, and will it be the same logic to go from E to A to F to B to E? Will it be the same logic, just using different,
Yeah, you have to figure out what sets the gate. No, it's a separate gate. I don't want to make it that complement, that hard. So let's give some symbols, right? The first symbol is a NOT gate, which has a 6 on it. It's a 6-state NOT gate. Okay,
Okay.
that's easy. This is easy, right? The next one is a
6.
half complement gate. It's a half NOT gate. So, and we need to say, or another way to say is 90-degree about z-axis. So that rotates states 90-degree about z-axis. So it takes x minus x, x plus y minus x minus y, and rotates them to plus y minus x minus y plus x. Okay, and then we have another gate which is
What is this one?
about y
Okay.
and then about z. Okay,
Okay.
so
And-
this is what you need to invent,
Got it. Okay.
and this will go into the submission.
And so that's all one paper.
This is one paper.
Okay.
So one NOT gate and then 3 rotation gates about different axes.
Yeah.
Okay.
And then do the other three the other 2 rotation gates have a name as well?
Other 3 rotation gates, we should just call them half complement about x about z, half complement about y, half complement about z.
Wait, were you asking if there's different logics for each of the half complements for an X?
Yeah.
Yeah. That's what
This
I was
is a physically a different circuit, physically a different circuit, and physically a different circuit.
Okay.
And then you would have a different type of gate, which would have complement, but then it will take the rotation angle about it, right? If you invent this, I would bend to you guys. So
Wait. Could you explain that one more time?
so rotating about z, y, and x, these are 3 separate gates, right?
Mm-hmm.
I can make the fact that rotating about what as a input to the gate.
Oh, so okay.
So this is now a universal rotation gate. You can have that, just like the Rubik's cube that Manu was showing, right? You tell the gate rotate about x, and then it rotates about x. Then next time you can say rotate about y, then it rotates about y. Next time you say rotate.
So it takes 2 inputs.
And
A
it's all
rotate-
in one circuit instead of 3 separate ones.
Yeah, if you do all it in one circuit where it's reconfigurable, then I'll give it up to you.
Okay, can you give a list of what we can do? Like, because I never understood that.
Wait, could you go back to the
You should like
previous page?
inject,
There
extract.
is one more phenomenon I need to add to tell you what you need to do, but I will do it next week. This is already way too much for one class.
Okay. And then during class today, are we just gonna watch the lectures as well?
So rest of the class, I want you to take turns going through this PDF. Let me download this.
Okay.
And then explain each other. How do I do that? Okay, I'm going to email this to you. I should have started a new PDF. Okay. How do I do this? Okay. I need to just take screenshots and post it in. Worry, what do you think?
It's a lot of information.
I know you are like you're joining when the harmony, like the orchestra is like coming all together. We
So
haven't
should I-
done this topic before, so that's a good thing. But I can see that this is, you need to revise this, like,
Yeah.
and then ask a lot of questions.
So actually on the, like, I think, yeah, it says nanohub.org. There's four or five papers there. Which one?
Yeah,
Which one?
I want you to revise the lecture today, like what we did today, and then
Oh.
listen to the Supriya Datta video.
Okay.
Um,
But then on my own time, I'm interested. I just want to read these papers. Should I read all of them, or is there a specific one? Which you want?
just download them, see what you can follow,
Okay.
right? Um, let me start recording.